WAEC 2024. Let's take this question. It says, which of the following terms has different dimension from the other? So they are asking us to find the dimension, the unit dimension or dimensional formula for each of these terms or physical quantities or combined physical quantities, and then see the one that is different from the other. So there is a negative equation, which means out of these four, three will have the same dimensional unit, and then the one that doesn't have the same will be the answer. So let's start. Let's start with the first one, stress times strain. Stress times what? Strain. Now, the mathematical definition for stress is force, the unit what? Area. I know that you know that pressure mathematical definition is what? Force per unit what? Area. But still, both of them have a difference. There is a difference between pressure and stress. When you're talking about pressure, you are talking about force applied per unit area on a surface. That's if you have a surface, this is the surface. How much force is being applied on that area? Then that's pressure that you call it. Then for stress, stress happens within the body of a material. So if you have a body that like this, within the internal molecules of this material, what kind of pressure is it giving out on this material? You understand? When subjected to certain things like heat or being beaten or being stressed, like in elasticity. So when you draw a material, try to stretch out a material, the pressure you are attaching there is actually called a stress, because you are stressing that thing. It's just like saying that someone is stressing you out. Understand? That means the person is drawing out a lot of strength from you, or energy from you. So stress happens within, while pressure happens externally, while stress happens internally. Okay, so let's go back. So stress is force per unit area times strain, and then this one is strain. The mathematical definition of strain is extension over length. That's extension per unit length. So let's find the dimension for this combination. Dimension will be, we define force. Force is mass times acceleration. Area is length times length. So the dimension of area is L raised to the power of 2. And then here, extension is a length on its own. Original length is also a length, so they will cancel out. What is left is what? Mass times acceleration over L squared, which is what? Stress. That's F over A. So mass, dimensional unit for mass is capital letter M. Acceleration, which is velocity over time, which has the dimension of L over T squared. Acceleration here will be L T raised per minus 2. That's if you take T raised per 2 to the top, it becomes raised per minus 2. So that's acceleration. Then over this L squared here. So this one L will cancel one of the L's here. Here is L times L. So one L will cancel. So one L is left here. So what is now left is M L raised per minus 1. This one that is left, if you take it to the top, it becomes minus 1. And then T raised per minus 2. So this is the dimensional unit for this first combination, which is stress times strain. And funny enough, this dimensional unit is also represent for pressure, because when you say pressure is also defined as what? Force over area. That of strain cancelled out here. So the actual dimension that we found is also the same as that of pressure. So pressure has the same dimensional unit as stress. So now A and C are the same. So let's look at B. B says stress divided by strain. Now stress is what? Force over area, then divided by strain, which is extension over original length. Now, if you do your mathematics, division of fraction, this is F over A times L, that's original length over extension. So this one, the dimensional unit for original length is L, and the dimensional unit for extension is still L. So they will cancel out. So you are still left with what? Force over area, which is the definition of stress or pressure. So it will still have the same dimensional unit there. ML minus 1, T minus 1. So A, B, and C have the same dimensional unit. So without even bothering further, I would say that torque D is the answer. Which of the following term has different dimension from the other? So D will be the answer. D will have a different dimension. But however, let me just find the dimensional unit for torque. Find the dimensional formula for torque. So if you define torque, torque is defined as the product of force times perpendicular distance. Force times perpendicular what? Distance, which is what? F times L. So force, which is mass times acceleration, acceleration is length times that minus 2, then times this perpendicular length here, which is L, will be equals to ml squared t minus 2. You see that this one here is different from this one here. So torque is the one that doesn't have the same dimension as that. And torque has the same unit as what? Work done. And also have the same unit as what? Moment. So torque is defined as the moment of a couple. So there is a tutorial on that where we'll be doing equilibrium of forces. Then we look at moment. So the answer to this question is D. Thank you. JAMB 2020. Let's take this question on dimensional units. Which of the following is the dimension of pressure? So first, let's avoid confusion in things that has to do with units, because basically unit is physics. So take for instance, if you are to measure a length, the SI unit of any form of length, whether you call it a height or you call it a distance, or you call it height, call it distance, call it length, call it breadth, whatever you call it, so far is just from one position, a straight line position, or whatever kind of line position. So length, the unit for length is meter. That's the SI unit for length. And then the dimensional unit, that means at the core basic of it, what is actually the unit of length is a length. Take for instance the dimensional, you might see that we might have height, you have distance, you have displacement. all those language, their units are the same, and their dimensional unit is what? Length, L, represented with capital letter L. So if you take a quantity, derived quantity like area, area is length times breadth. But at the core point, this is length times what? Another length. So the dimensional unit of area is what? L squared, capital L squared, length times another length. You understand? So that's what we mean by dimensional unit. So now, which of the following is the dimension of pressure? Before you're able to determine the dimension of pressure, first you have to be able to define pressure mathematically. Pressure is defined as the ratio of force per unit what? Area. So pressure is talking about the amount of force you exert on a certain area. This is the area and this is the force. So that's the definition of pressure. So how much force do you exert on an area? That defines pressure. So what pressure has so many units, but at the fundamental form, the unit of force is what? Newton, and the unit of area is what? The unit of area is meter square. So the unit of pressure is what? Newton per meter square. But the question here is we should find the dimension of pressure. That's the dimensional unit. So this is the SI unit of pressure. So we are now to look for what? The dimensional unit. So that means at the core or the very foundation of this quantity, pressure, what are the fundamental quantities involved? At the core foundation of units, what we have is mass, length, and time. This is the three basic. Though recently they've added capital letter I, which is current. So this is but the three basic dimensional unit is what? Mass, length, and time. That means every other unit that you think of contains these three units. So now let's find the dimensional unit of pressure. So now, first we have to find out of force. Force is defined as what? Mass times acceleration. Then divided by area. Area is defined as what? A length times another length. A length times another length. So if we continue to split that, so mass, the dimensional unit of mass is capital letter M. Capital letter M represents what? Mass. So we've written it down there, times. If you break down acceleration, the definition of acceleration is what? Velocity over time. Then remember, over what? Length times length. That's L raised to the power of 2. Now, if you split this velocity into its dimensional unit, this is mass. Velocity is defined as displacement over time, and displacement is a length. So that's like saying a length over time, over another time, then over L squared. Hope I'm not getting anyone confused or making it cumbersome. So this will now be mass times, if you process this, you will have length divided by time squared, then divided by L squared, which is the same thing as here, M times length divided by L squared times T squared. This is mathematics. I also have videos on processing fractions on math. So this L here will cancel one of the L. You know, there are L times L here. So this one of this L will cancel one of it. So you are now left with L m divided by L times T squared, which is the same thing as m. If you bring L to the numerator, that will be L raised to the power of minus 1. And if you bring T squared to the numerator, that will be T raised to the power of minus 2. So the dimensional unit of pressure equals to mL minus 1 T minus 2. So what option is that? Option A. Option A. Thank you. JAMB 2015 under measurement and unit, dimensional unit. So the question says, at what respective value of A, B, and C would the unit of work, the joule, be dimensionally similar to m raised to the power of A, L raised to the power of B, T raised to the power of C? So the question here is simply asking us to find the dimensional unit of work. Work is a physical quantity. Theoretically, work is energy. Work is amount of energy put to do something or to get things done. But in physics, we define work as the product of force times what? Times distance. So if this is a mass on a floor, call it a 50 kg mass. Now, if you talk about work and there is somebody here who wants to lift up this 50 kg mass, work done will be what? The weight of this mass here. You know, weight is the same thing as force. Force is weight. Work done here is the weight of this mass here times the distance this person is going to carry it to cover. You understand? So if this person lifts up this mass from this ground up here, maybe say 5 meters. Let's say the weight of this mass is 50 Newton. 50 Newton. So if this person is able to lift this mass up here up to 5 meters, the work he has done in lifting up this mass will be what? 50 Newton times 5 meters, which will be 250, which will be 250 this thing joules. The unit for work is joules or Newton meter. That's, unit of force is Newton, and unit of height or distance is meter. So the unit of work is either you call it joules or you say Newton meter. So that's it. But now they are looking for dimensional unit of work. When you talk about dimensional unit, you are trying to see the very core parameter that makes up the unit of work. So we are going to split this force into its dimensions. Force on its own is defined as mass times acceleration, then times this distance here. Now the dimensional unit of mass is represented by letter M, capital letter M. Then the dimensional unit for acceleration, you remember that acceleration A equals to what? Velocity over time, t. And velocity on its own means what? Displacement, or you can say distance, d over time, over this other time here. So that if you process that, you have d over t squared. The dimensional unit for distance or displacement, that's at the core foundation. What is distance? What is a distance? A distance is a length, a height is a length, displacement is a length. So this is L over what? T squared. So the dimensional unit for acceleration is L over t squared. So this is m times the dimensional unit of acceleration, which is L over t squared. This is distance. And what is the dimensional unit for distance? That's the at the core foundation. What is distance? What is it? Is a length. Distance is a length times L. So if you multiply that, it will be m. L times L is L raised to the power of 2 divided by t squared, which equals to m L raised to the power of 2. This t that is on the denominator on the bottom of the fraction raised by 2. According to law of indices, if you take it to the numerator, the power will become negative. So that will be t raised by minus 2. So if you compare what we have here with m raised by a, L raised by b, and t raised by c, you find out that our a equals to, this m is raised by 1, equals to 1. And our L, which is b will be equals to 2. And c will be equals to minus 2. So that is 1, 2, minus 2, 1, 2, minus 2, option B. So that is how to find the dimensional unit of any physical quantity. That's how to find it. So the key to this is being able to define the unit mathematically or in physics form. You understand? If they said find the dimensional unit of area, if they said find the dimensional unit of area, area by definition equals to a length times another length, or even if you say breadth, a breadth is still a length. You understand? So length times length, that will be L raised to the power of 2. So that is, so being able to define a quantity is the key to knowing how to derive the dimensional units of that quantity. Thank you. 2015 on measurement and unit, on dimensional unit, we on dimensional unit. So the question here says the dimension of the universal gravitational constant is, so we are looking for the dimensional unit for universal gravitational constant. So first, I said that the key to knowing the dimensional unit of any quantity is to know how, the definition, the mathematical definition of that quantity. So here we are talking about universal gravitational constant, which come from Newton's law of universal gravitation, which states that the force between two bodies or two masses, the force between two bodies or masses is directly proportional to the product of the masses, m1 times m2, and inversely proportional to the square of their distance apart. So this is a variation now. So when we bring a constant of proportionality, that will be f will now be equals to m1 m2 over r squared. R represent the distance apart, the distance between the two masses, then times the constant k. So now this question is asking us to find universal gravitational constant, the dimensional unit for it. So this is our universal gravitational constant here, k. So we are first going to make it the subject of the formula. If you make k the subject of the formula, k will be equals to, here r is on the denominator. So if you do cross multiplication, f here will multiply with r. So that will be force times what? R squared. And then since this one is on the numerator here, if you divide both sides by m1, m2, here will be that divided by m1, m2, making k the subject of the formula there. So now we've successfully made a gravitational constant the subject of the formula. So what we are now going to do is to derive the dimensional unit for this constant. So let's start. Dimensional unit for force. Force is a derived quantity. So first I'm going to split that of force. Force means mass m times what? Acceleration. Acceleration a. Okay, then times r squared. The dimensional unit for mass is m. Another mass is another m. So acceleration, the dimensional unit for acceleration is defined as what? Change in velocity over time. And velocity on its own is a derived quantity or a derived unit. It's a derived quantity. So velocity on its own means what? Displacement or distance over time, then divided by another time. So this will be distance divided by time squared. So the dimensional unit for acceleration will be what? The distance in its dimensional unit is L, is a length, over time is represented with capital letter T over T squared. So if we represent that here, we will now have mass times acceleration will now be L over T squared times r squared. R is a distance, so it's represented by L. Distance times another distance, that's L raised power of 2. Then divided by m times another m. M times another m. So if we proceed, this will now be m times L squared divided by m times m times t squared. This t here on this bottom here, according to where we process fractions, in which I have videos or tutorials on processing mathematical fractions or operation on fractions. So this t here will come down and join this one here. So now this m here will cancel one of the m here. So what is left is now L times L squared is L raised power of 3 divided by m times t squared. So if you take everything to the numerator, that will be m here is raised to the power of 1. So when it goes to the numerator, it becomes m raised to the power minus 1. L remains where it is, L raised to the power of 3. And t, if it goes to the numerator, it becomes t raised to the power minus 2. So the dimensional unit for universal gravitational constant is m raised to the power minus 1, L raised to the power 3, t raised to the power minus 2. So let's see which of our options lie with that. Minus 1, 3, and minus 2. Minus 1, 3, and minus 2, option A. So option A is the correct answer to that question. Thank you. Welcome, JAMB 1997, under dimension of units. It says, at what respective values of x, y, and z would the unit of force, the Newton, be dimensionally equivalent to m raised to power x, L raised to power y, and t raised to power z? So this question is asking us to find the dimensional unit or dimensional formula for force. Remember, when we say when it is said that we should find the dimensional unit of a particular physical quantity, what they are asking us to do is to find how the units relate to these three basic fundamental quantities, which is mass, length, and time. So now, when we write force, the unit for force is Newton. And then the mathematical definition of force is what? Mass times acceleration. So we're going to see how we extract, how we get mass, length, and time from the formula of force, from the mathematical definition of force. So already, definition of force is what? Mass times acceleration. So mass on its own has been represented here. So we write here m. Then acceleration, we are going to look into acceleration to see the fundamental units or quantities that make up this acceleration. The first step is to define acceleration in its mathematical form. Acceleration means what? Velocity over time, the rate of change of velocity. And then we move further. This is mass times, we have to also velocity here is not in its fundamental form, fundamental unit. So we have to also find fundamental unit of velocity. Velocity, the mathematical definition of velocity is what? Change of displacement or distance over time. So the fundamental unit of displacement or distance or height is what? Length. Is a length. So a displacement, a height, and distance is a length. So time remains time, capital T. So the fundamental unit for velocity is what? L over T. So if we come here and replace that, in place of B, we now write L over T over this other T that was there already. So this will be equals to M times L over T squared. So this will be M raised to power 1 and then this is L raised to power 1. If you take T to the numerator, it will be T raised to power minus 2. So the dimensional unit for force is ML T raised to power minus 2. So the values for X, Y, and Z, X will be equals to 1, Y equals to 1, and Z equals to minus 2. 1, 1, minus 2. Option B. Thank you. Alright, welcome. In 1996, the under unit dimension of units, or you can say dimension of physical quantity or dimensional unit. Okay, the dimension of surface tension is, so we should find the dimension for surface tension. Like I usually say, that to find the dimensional unit for any physical quantity, the first thing you have to do is to define that quantity mathematically. So the definition of surface tension is, it is the ratio of force to length, or you say force per unit length. So that is force over length. That's the definition of surface tension. Surface tension means, for instance, if you have a length here, tap, 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 how much force is being exerted on, or that is being, pushed out from a unit of that length. How much force is it giving out or receiving? So that's surface tension, the one that makes water to stick to a wall or something of that nature, membrane. So let's continue. So surface tension is what? Force per unit length. So now we are going to find the dimensional unit for each of these other quantities. Force on its own, if you define it, is what? Mass times acceleration, A. Length. The dimensional unit for length is capital letter L. So we continue. So Mass, dimensional formula for mass is m. Acceleration, the definition of acceleration is change in velocity with respect to time. And the definition of velocity is what? Change in displacement or distance with respect to time. Then over time here, so that you have distance over time squared, and the dimensional this thing for distance is L, and dimension for time is capital letter T, so T squared. So here the dimension for acceleration is L over T squared, then divided by this other L here. So we do that properly, you have m L T raised power minus 2 divided by another L. So that final answer will be, when this L on this bottom goes to the top, it becomes raised power minus 2. So it will be m L minus, no, sorry, this one will cancel this one. And then what you will have is, m T minus 2. This question on dimension of unit. For which of the underlisted quantities is the derived unit m L raised power 2 T raised power minus 2 correct? So we are to find the quantity that has this as its dimensional unit or dimensional formula. So quickly, what we're going to do, we're going to take each of these quantity, define them mathematically, and write their dimensional formula and see the one that relates with this. That's how we know our answer. So finding the dimensional formula or unit of a quantity means that we should find how mass, length, and time relates to that physical quantity. That we should find how these three main fundamental quantities relate to that quantity. Okay, so let's start with moment of force. Moment of force is defined as the product of force times what? Perpendicular distance from line of action. So that's the definition of moment of a force. And then force on its own, if you split it further, the mathematical definition is mass times acceleration, then times what? This distance. This sign here represents perpendicular. Don't mind me, represent perpendicular. Okay, so times what? Distance. So mass here, its dimensional unit remains m. Then acceleration A is defined as what? Velocity over time. And velocity on its own is defined as what? Displacement or distance over time. Then another over time. So distance, the dimensional unit for distance is what? Length. Distance is a length, and time remains time. So there are two times here, that will be T raised power 2. So mass times acceleration will be L over T raised power 2 times distance is L. So this will be L times L will be L squared over T squared. If you take this T to the numerator, it becomes minus 2. So you see that moment of a force has this as its dimensional unit. So I is there. So let's see work. Let's find the dimensional unit for work. So dimensional unit for work, first, before you find the dimensional unit, you have to define a quantity first. Work is defined as a product of what? Force times distance covered. So you see that work has almost the same definition as movement. The only difference is that in movement you are talking about perpendicular distance. That's distance that is in 90 degrees from the line of action. But when you say work, what we are considering is the product of force and distance, whether it's perpendicular or not. So that's the only difference between movement and work. Movement and work have the same unit. Okay, so since it's the same, it will still go with the same analogy. So the dimensional unit for work will be what? ml squared t minus 2. So let's do for that of acceleration. Acceleration is defined as what? The change in velocity with respect to time. We already did that, and we've seen here, and we've seen that acceleration dimensional unit is what? L t raised power minus 2. So which is not the same with here. So you see that moment and work have this as their dimensional unit. Acceleration dimensional unit is different from this. So the answer is I and II, option C. The answer is I and II, option C. That is moments of force and work. They are the ones that have this as their dimensional unit. Thank you.